All right, hello and welcome back. Today we're going to be doing Bolzano's theorem and the intermediate value theorem. So I'm going to start this off by giving an example. So consider T to be time in minutes and capital T to be your temperature in Celsius, degrees Celsius. So consider an ice cube that starts at -50 degrees Celsius and it starts slowly melting until it reaches 20 degrees Celsius after 12 minutes. Now, all we know is that assuming that it is continuous, it does continuously melt. It doesn't just disintegrate like rapidly or anything. It does actually rate at a, oh sorry, melt, not at what is it? It's continuous basically. So you don't have any holes or gaps or discontinuities. Must there be some time when the temperature is 0 degrees Celsius? So when it's at the melting point exactly, right? And the answer is yes. And why? Well, we'll come back to this thought. So first, we're going to let the set S be the following, and I'll show you why that is all important. And we'll let X not be the supremum of S. But wait, remember that the supremum is the least upper bound of a set. So an upper bound, so it's greater than all of the elements. That's the least upper bound. There's no upper bound that's less than it. So what does this all mean? So we're considering the set S of all x in this interval from A to B. Sorry, this is f of A and this is f of B. But really, we're saying that um, we're considering this interval, but only the x's with positive outputs, right? And what is the supremum of this? First, is the supremum, does it exist? And secondly, is it positive, negative, or zero? Is it positive? Well, if it were positive, then there would be some interval by the continuity lemma around it where you have more outputs that are positive. But wait, that would be elements in S that are greater than our supremum, which is a contradiction because remember, x naught we said is our upper bound. There are no elements greater than x not in S, but that's a contradiction. And over here on the other side, what about if x naught is negative? Well, we still have a contradiction nonetheless because we'd have to have some interval, right, by the continuity lemma where all the values, all the outputs of the x's are negative. But what would this imply? Well, this would imply that to the left of x naught, there's some value, right, that's negative, but that value, which is less than x naught, is also an upper bound of S because there are no values that are greater than that that are in S. So if you're understanding what I mean, it's like this x naught minus delta or some value. Like here would be a better candidate for your supremum and it would be an upper bound less than x naught, which is a contradiction. So f of x naught is 0. So let's completely formalize this and write the proof. Bolzano's theorem basically states that if a function is continuous over the closed interval a comma b, and f of a times f of b is negative, so their signs are different, then there has to be some x naught in the interval a comma b such that the f of x naught is 0. So it has to cross the x-axis at least once. Now, note that this is a theorem of existence, but you're not actually finding it. You're just proving that it exists. Now, first we're gonna consider our set S to be the same set that we already said, and S is non-empty because either A is in S or B is in S, right? And S is bounded above by B since we already know S is a subset of this interval, and the furthest right endpoint is B itself. By the completeness of Reel's theorem, S has to have a supremum, and we'll let that supremum of S be x naught. So we'll consider case 1, which is where f of A is greater than 0, is greater than f of B, but case 2 is trivial once we have this under your belt. So case 1.A, toward a contradiction, we'll assume that f of x naught is positive. And then by the continuity lemma, like we said, there exists some delta greater than 0, such that for all x in that delta neighborhood around x naught, the outputs are all positive. Thus, you have some elements in S because positive outputs, and in this x naught comma x naught plus delta, but this contradicts x naught being an upper bound of S, so our original assumption was wrong. Case 1.b, towards a contradiction, assume f of x naught is negative, then by the continuity lemma, there exists some delta greater than 0, such that for all x in x naught minus delta to x naught plus delta, your outputs are negative. Thus, in the left neighborhood around x naught, there are no elements of s, but then x naught minus delta, or like some value, right? X naught minus delta over 2, let's say, is also an upper bound of s because there are no elements to the right of it. And yet x naught minus delta is less than x naught, which is a contradiction. Really, formally, if you're talking about it, you can reference the supremum lemma and say how it's a contradiction, because if x naught is a supremum and x is some positive real, or not positive, but some number less than the supremum, you have to find a value between, or else the number you found is a better candidate. Not necessarily a supremum, but a better candidate for the supremum. So f of x naught is also not zero, or sorry, non-negative. So f of x naught is non-negative and non-positive, meaning the only thing that it could possibly be is zero. And we know x naught is not A, x naught is not B, so we have our conclusion. But this is only for case one. However, case two is trivial by considering g of x to be negative f of x. Now, g of x is continuous itself, and g of a is greater than 0 is greater than g of b, but we can just use case one now. And that means that, yeah, there is some value of x naught in this interval, such that g of x naught is 0, which is negative f of x naught, so f of x naught is 0. So this completes our proof of Bolzano's theorem. And back to our problem, we can apply Bolzano's theorem. If you don't remember, I wrote it here. Yes, since it's continuous and one output of the endpoint is positive and the other output of the endpoint is negative, it has to cross the x-axis. There has to be some time when the temperature is 0 degrees Celsius. Who cares when it is, but it has to happen. Now, the intermediate value theorem, or the IVT, is really just Bolzano's theorem, but more general. The theorem states the following. If f is continuous on a closed interval bracket a comma b bracket, and f of a is not equal to f of b, and k is any number strictly between f of a and f of b, then there exists some x naught in a comma b such that f of x naught is equal to k. Now, visually, it makes sense, right? Very similar to Bolzano's theorem. If you go from f of a to f of b, you have to cross k sometime. So proof, we'll just let g of x, right, be the difference of f of x and k. Now g is continuous because f and k are continuous, and without loss of generality, we'll say that k is that's our f of a is less than f of b, right? And we could do the opposite direction, but it's the same thing. Say f of b is less than k is less than f of a, but we'll just subtract k from both sides, but notice f of a minus k is g of a, and f of b minus k is g of b, so we just have here. But this is the direct application of Bolzano's theorem that we already know how to do. So there is some x naught where g of x naught is 0, which is f of x naught minus k, which is, of course, f of x naught is equal to k. Then here's an application. Consider the following graph. Your graph of time and your height in respect to time. So, basically, what you have here is, let's say there's some point where you're at 10 meters and some point where you're at 1,000 meters. And let's say that you are ascending in a continuous manner. You're not jumping from one place to another. There's no discontinuities, right? Not necessarily that you're climbing at a uniform rate, but that you're climbing continuously. So in that case, can you say that there's some point, right? Some point in time you're at exactly 100 meters? And the answer is yes, by the intermediate value theorem. Maybe that point is here, but we're just saying that it's between 10 meters and 1,000 meters, right? So yeah, there is some point where you were going exactly 100 meters. Hopefully this helped. This will be the last video I will make, most likely for now, on continuity and limits, but after this, I'll move on to derivatives, right? Next video will most likely be introduction to derivatives. So good luck.